Hello everyone. Welcome to our channel. Today we're going to start the Calculus for Non-Specialists full course. This course is designed for non-math, non-physics, and non-engineering undergrad students. However, everyone may benefit from the materials covered in the course. The course is composed of three main parts: Calculus 1, Calculus 2, and Calculus 3. Let's begin with Calculus 1, and here is the first lecture of Calculus 1. If you are new to the channel, make sure to subscribe and turn on the notification bell, so you won't miss future episodes. Keep in mind that the aim of this channel is to represent the beauty of mathematics and physics, and the pure connection between them. So, watch other videos on our channel, and support us with your comments and suggestions. Before we actually start talking about calculus, it's worthwhile to review over two important prerequisite subjects: the basics of mathematical logic, and the basics of set theory. This review session will help us a lot and make our lives easier later on in problem solving. First, let's talk about the basics of mathematical logic. In order to understand mathematics and utilize it in everyday problems, we need to set up a bunch of rules. The first thing we need is to identify a formal language to express the concepts and a set of logical components to rationalize arguments. That is why we need to know the logic in mathematics. Logic is the analytical theory of the art of reasoning. Exploring the applications of formal logic to mathematics is called mathematical logic. In other words, it is how we formalize the logic that we use in our proofs. In logic, a set of symbols is commonly used to express logical representation. So, as an essential point for mathematical logic, a formal language is fixed to be used. On the basic part of mathematical logic is propositional logic, which is composed of 1. Logical prepositions and 2. Logical connectives. Propositional logic is a formal mathematical system, with rigidly specified syntax, for reasoning about propositions and how they relate to one another. Now, let's see what is a logical proposition. A proposition is a statement that is, by itself, either true or false. For example, Monday is the first day in a week is a true statement, but Canada is in Asia is a false statement. Note that statements like commands, questions, and gibberish cannot be true or false, so they are not prepositions. So, how are you? Or go to sleep, or doops, let's dance, are not propositions. Well, it's time to set a symbolized formalism. In mathematical language, we can identify a proposition with a letter, or symbol, which is called the propositional variable. For example, A equals today is Thursday, then we may say A is true or false. Propositional logic enables us to formally encode how the truth of various propositions influences the truth of other propositions, determine if certain combinations of propositions are always, sometimes, or never true, or if certain combinations of propositions logically necessitate other combinations. The question is now, how do we connect logical propositions? And the answer is, with logical connectives. We can connect two or more propositions to make a new combined statement and check that if the new one is true or false. We connect the logical propositions with logical connectives. Each of the combined expressions is called a formula. In other words, every statement in propositional logic consists of propositional variables combined via logical connectives. Each variable represents some proposition, and connectives encode how propositions are related. When we connect two propositions, the new proposition may be true or false depending on the truth of the primary propositions. Thus, each logical connective can alter the truth of logical propositions. In order to show these alterations, we use a table to show when the new proposition is true and when it's false corresponding to the truth of the primary ones. This table is called the truth table. Now, we're in the right position to see some basic logical connectives and their truth table. The first logical connective that we're considering is the simplest one, the logical not. This connective is employed to negate a proposition. Often, it is recognized by a symbol. Its truth table is very simple. Whenever a proposition is true, its corresponding logical not proposition is false and vice versa. So, if proposition A is true, then proposition, not A, is false, and if proposition A is false, not A, is true. Let's check an example together. We define proposition A to be, 4 is a prime number. Then, proposition, not A, is, 4 is not a prime number. Therefore, we can claim that proposition A is false, and proposition, not A, is true. Also, be aware that negate of the negation of a proposition is the same as the original proposition. It means that double negation does not change the truth of a proposition. The next logical connective is called logical and, also known as logical conjunction. This connective, as its name suggests, is used to add information to a statement. In other words, it makes a bridge between two or several propositions to logically connect them. This connective is often symbolized in various ways as you see some here. The resultant proposition of two propositions combined by an connective is true, if and only if both propositions are true. So, we can easily construct its truth table. Consider two propositions which we call the first one A and the second one B. Depending on the truth of each of them, we must consider four cases. If the proposition A is correct and the proposition B is correct, then the resultant proposition, A and B, is correct. The resultant proposition, A and B, is false for the other three cases since in all of them at least either of A or B is false, as you can check them on the truth table. Let's see two examples about the connective and. As the first example, consider the following propositions. The proposition A is, 4 is a prime number, and, the proposition B is, negation of A. A is a false proposition and B is a true proposition, so the resultant P position, A and B, is a false proposition. Obviously, the in combination of a proposition with its negation is always false because either one of them is false. For the second example, consider that, proposition A is, USA has 50 states, and proposition B is, January is the first month of the year. We see that both propositions are true, so the resultant proposition, A and B, is true. The next connective that we're going to define is the logical or, also known as logical disjunction. It's sometimes called inclusive or as opposed to exclusive or that we'll talk later. This connective comes with several symbols in different notation systems as you can see here. The or combination of two propositions is true if at least one of the propositions is true. So, we can simply identify its truth table. Similar to the and connective, because we are combining two propositions, we have to consider four cases. When both propositions are true, the resultant is obviously true. If one of them is true and the other one is false, the resultant is also true. If both of them are false, the result is false. Let's see some examples. Consider the or connection of a proposition with its negation. If a proposition is true, its negation is false, and if a proposition is false, its negation is true. In either cases, at least one of them is true, so, the or combination is true. Now, consider A to B, 8 is a prime number, and B to B, 3 is not a prime number. Both of these propositions are false S and D, so is A or B. So far so good. We already discussed three of the most common logical connectives. Let's introduce another one. The next one is called XOR, also known as exclusive disjunction. You might have heard it as exclusive OR. There are several notations for this one as well, as you can see some here. The XOR combination of two propositions is true, if and only if one of them is true and the other one is false. That's why they call it exclusive OR. So, as usual, we can easily identify its truth table for all four possible cases. If A and B are both true, then A XOR B is false. If A is true and B is false, then A XOR B is true. If A is false and B is true, then A XOR B is true. If A and B are both false, then so is A XOR B. Let's discuss some examples. The first one is the XOR combination of a proposition with its negation. Clearly, the result should be always true since the two primary propositions have opposite truths. For the second example, consider that proposition A is, 2 is an even integer, and proposition B is, x squared equal to 0 has a solution of x equal to 0. So, both statements are true. Thus, the statement A XOR B is false. The next logical connective we're going to talk about is an interesting one. It's called logical implication. As its name suggests, we use this connective to show that the truth of the first proposition implies the truth of the second one, or the truth of the second proposition has resulted from the truth of the first one. It is more often regarded as the if and then connective. It means that if something is true, then the other thing is true, too. In other words, you assume that a statement is true, and then based on that assumption, you make a true conclusion. There are two most common symbols for logical implication, as you can see. We read it, A implies B. Whenever you saw it in the reverse direction, it reads, A implied by B, which is the same as, B implies A. Now, let's identify the truth table of the logical implication connective. If the first proposition is true as well as the second one, we realize something true implied something else true. So, this is a true statement. If the first proposition is true, but the second proposition is false, we see that a true fact yields a false result. So, we understand that the whole statement is absolutely not true. If the first proposition is false, but the second proposition is true, we see that a true fact has resulted from a false assumption. That might be possible. So, we recognize that the whole statement is true. It's like somehow a haphazard true result has been generated from nowhere. So, that doesn't mean the whole statement is not true. The last one is a good one. If the assumption is wrong, or is a false proposition, and the conclusive proposition is false too, the whole statement is true. It means that a false assumption has given a false conclusion. Kinda confusing, right? This is very important. So, it's worthwhile to clarify it more. Notice that logical implication says nothing about what happens if the first proposition, or the assumption, is false. It does not say anything about causality. It just says that if the assumption is true, the conclusion will be true as well. The only way for R implies S to be false is if we know that R is true, but S is false. So, if your assumption is true, you have to make a true conclusion. If R is false, the statement R implies S does not guarantee anything. It is true, but it is not meaningful, not making sense. As an example, consider the implication of a proposition to its negation. Well, if we construct the truth table, we see that if A is true, then not A is false, so A implying not A is also false. It's like we say if 3 is an odd number, then 3 isn't an odd number. This is absolutely a wrong concluding remark. On the other hand, if A is false, then not A is true, so A implying not A is true. Does it make sense? It's like we say if 3 is an even number, then 3 isn't an even number. Well, 3 is not an even number regardless of our wrong assumption, so the implication relation is not false. Let's see another example. Consider proposition R, which is, 5 is an even number, and proposition S, which is, 6 is an odd number. Obviously, both of the propositions are false, but the combined statement of R implying S is true. Well, in a bizarre world where 5 is an even number, then anything else may be true. Isn't that right? Finally, I'd like to point out that it makes much more sense if, in the truth investigation of a combined statement with the implication connective, we focus more on the implication connection rather than the propositions. I think now the point is clear, so let's move on to the last logical connective. This connective is called logical biconditional, and it's somehow an extended version of the previous one in both directions. So, it's also known as two-way implication connective. It means that the first proposition implies the second one and vice versa. That's why it is used for if and only if expressions. Both propositions result from each other. The symbols used for this connective are two-way implication signs. In the relation, A if and only if B, A is true if and only if B is true, or B is true if and only if A is true. Simply, if A is true then B is true, and if B is true then A is true. So, in the truth table, we get a true value for the resultant statement if both propositions have the same value, and we get a false value if the propositions differ in truth values. From the truth table, we intuitively learn that logical biconditional says either both A and B are true, or neither of them is. So, one may interpret logical biconditional as equality. The two propositions must have equal truth values. For example, if proposition A is, 3 is an odd number, and proposition B is, 5 is an even number, then, the statement, A if and only if B, is a false statement since A is a true proposition, but B is a false proposition. However, if we change proposition A to, 3 is an even number, then, the statement, A if and only if B, is a true statement since both A and B are false propositions. Likewise, A if and only if B, is true if both A and B are true propositions. Very good. So far, we learned some of the most important and common logical connectives. But, We're not done yet. In order to turn logical statements into mathematical language, we need some other tools. Another very useful tool is called quantifiers. Learning from its name, it quantifies or enumerates statements. I introduced two of the most common quantifiers here, known as universal quantifiers and existential quantifiers. Let's see what they are about. Universal quantifier has a symbol like a vertically inverse capital A, which I'm sure you've seen before. Literally, it means for each, or for all. This quantifier is basically used to generalize or extend a proposition to all members of a group or category. For example, if we want to assign an expression to all positive numbers, we can write, for all x greater than 0. Or, if we want to assign a statement to each member of real numbers, we use this quantifier and read, for each real x, or for all x belonging in real numbers. Look at this example. All positive numbers are greater than 3. We can use the universal quantifier to assign the statement of being greater than 3, to all members of positive numbers. We can easily check the truth of this expression. This proposition is a false statement since we can find a positive number like 2 which is not greater than 3. Let's talk about the existential quantifier. More precisely, it can be narrowed down into 3 categories. The usual existential quantifier uses a symbol like horizontally reversed T. It literally means, there exists. The second type is called non-existential quantifier. It is symbolized by a dash or cross line over the existential quantifier's symbol. It literally means, there does not exist. And, finally, the third type is the unique existential quantifier. It is represented by an exclamation mark beside the existential quantifier's symbol. It's used to mention that there exists a unique type of something applied in a proposition, or there exists only one member of a group that can be assigned to a proposition. So, it basically excludes a unique member of a collection of things. Now, we are able to write logical statements in the math language. Let's see some examples. Consider the statement, there exists a number provided that this number is positive. We call the number x, then we start our mathematical statement by the existential quantification, and we say there exists x, such that x is greater than 0. Note that for the conditional expression we use the short form of such that. There are some other conventional notations to use as well. We may replace such that with a comma, or a colon, or a semicolon, or even with a vertical bar as you can see here. They all mean the same, which is the appearance of a logical condition, or an unconnective related statement. Let's see one more. We aim to write the expression, each real number is between two rational numbers, in the math language. So, clearly, the statement includes all real numbers, so we should use the universal quantifier. Then, we see an existence expression, so we use the existential quantifier. In the end, we express the condition. So, it's gonna be like this. For all numbers, belonging to the real numbers, there are two other numbers, which belong to the rational numbers, you see, 1 and 2 rational numbers. Such that, x is between the two rational numbers. Don't worry if you are not very much familiar with the concepts of the real number set, or the rational number set, or even the set belonging notion. We're going to talk about these in the next lecture, that is the second lecture of this course, which is about the basics of set theory. So far, we've learned how to write logical expressions with math language. As the last subject of this lecture, we're going to talk about logical equivalence. This topic will tell us if two propositional logic statements are equivalent or not so that they deliver the exact same logical point. In propositional logic, if two propositions P and Q always have the same truth values as one another, they are called logically equivalent. We denote this by P equivalent to or identical to Q. Note that connectives are a part of logic statements, thus, equivalence to or identical to symbol is not a connective, it's part of the math language syntaxes. Generally speaking, in order to show that two propositions are equivalent, the idea is to build truth tables for both expressions and confirm that they always agree. Let's see more details in an example. In this example, we're asked to show if the two given propositions, P implies Q, and the negation of Q implies the negation of P, are equivalent. So, basically, we have to present the truth table for each proposition and check with each other. For this, we draw a big table to analyze both statements at the same time. That makes it easier for us to compare the truth values. If you remember, we've done the left part of the table before. But, we'll do it here again. If P and Q are true, then so is P implying Q. We can complete the other side of the table corresponding to the truth values of P and Q. Since P and Q are both true, the negations of them are false. So, as we've seen before, a proposition that says, a false statement implies a false statement, is true. If P is true, then the negation of P is false. If Q is false, then the negation of Q is true. So, P implying Q is false because a true statement is implying a false statement. For the same reason, the negation of Q implying the negation of P, is false too. Go on. If P is false, then the negation of P is true, and if Q is true, then the negation of Q is false. So, since a false proposition is implying a true proposition, both P implying Q, and the negation of Q implying the negation of P, are true. Lastly, if P and Q are false, then the negation of P and the negation of Q, are true. So, we get true values for the remaining two as well. Now, we see that the corresponding truth values for the propositions in the question match exactly. So, the two statements are logically equivalent. This is actually a known fact. So, it's worth memorizing it. Later, we'll see the same kind of rule again in the language of set theory. With this, we complete the first lecture. Let's have a summary of what we've learned. In today's lecture, we learned about the basics of mathematical logic. We learned about propositional logic. We learned what a proposition is, what a connective is, how to combine propositions to make a compound proposition, how to check the truth of compound propositions. We also learned some math language components such as quantifiers, and how to use them to turn logical statements into math language. Moreover, we learned when mathematical logical statements are the same. Well, that's great. We learned so much. In the end, let's discuss some complementary examples to reinforce these foundations. The first question asks us to write some logical propositions into math language. Please give yourself a few minutes and write down the answers. Now, let's check your answers together. The first expression says, if P then Q. This is the usual implication relation which says Q is a fact resulted from the assumption P. So, we write P implies Q. The second expression says, A if B. So, if the assumption B is true, the proposition A is true too. Clearly, we should write B implies A. Expression C says, C but D. This means that C is true, but also D is true. So, it's about the addition of information. So, we write C and D. If it's not very clear, imagine that we're saying, the rose is red, but the grass is green. It's like we're saying the rose is red, and also, the grass is green. So, we are adding two logical statements. Expression D states, R only one S. So, obviously, if S is true, we conclude that R is true. It's the same expression as, R only if S, or, if R then S. So, we write S implies R. Item E says, there is no real root for the function x squared plus 1. So, it basically means that we cannot find any real solution for the equation x squared plus 1 equal to 0. So, we start with a non-existential quantifier to write, there does not exist an x belonging to the real numbers, such that x squared plus 1 is 0. Finally, item F states that, there is only one number that adds 3 to give 5. We hear a statement about the uniqueness of something here. So, we use the unique existential quantifier to write, there exists a unique number A such that A plus 3 is 5. Obviously, we all know that A is 2. Very good. Let's discuss the second problem. In this problem, we must prove if the statement, P implies Q, is equivalent to the statement, negation of P or Q. As we've seen a similar problem before, we need to write down the truth tables for both statements and check if they match. So, we draw a combined truth table for both. We've done the left half of the table for the implication statement before, so we just copy and paste it here. Now, we start to fill the right half of the table. If P and Q are both true, then the negation of P is false, and the or combination of a false and a true proposition gives a true proposition. If P is true and Q is false, then the negation of P is false, and so, the or combination of two false propositions is false. If P is false and Q is true, then the negation of P is true, and so, the or combination of two true propositions is true. If both P and Q are false, then the negation of P is true, and thus, the or combination of a true and a false proposition is true. So, we see that the truth values of both compound propositions match. So, the claim is solid. This is also a known fact, so it's worth memorizing. With this, we wrap up the first lecture. Hope you enjoyed it. If you did, please like and subscribe. Keep in mind that the aim of this channel is to represent the beauty of mathematics and physics, and the pure connection between them. So, watch other videos on our channel, and support us with your comments and suggestions. See you next time.